so in the last class we were looking at the election algorithms in tree networks, and we left the algorithm midway because of lack of time. So, we will start with that algorithm and then look at election in more general networks. So, for election algorithms for trees, we assume that the processes belong to a logical tree. So, they are nodes of a logical tree. A physical network is not necessarily a tree, and each node knows that it has certain number of neighbors. Again, we do not assume that we assume that each node has a unique ID. Right. So, it is a non-anonymous network. So, let us start with that algorithm. So, I had written down these in the last class. So, the algorithm uses these variables WSP, WRP, and then there is an array of variables. So, it is an array of booleans for each q belonging to the neighbors of P. So, the size of this array is the number of neighbors of P, and we have VP in which we will store the ID of the best process or the leader in the end, and the state of P is an enumerated type which can have the following values, that is, it can either be sleep or leader or lost, and initially the state of P is sleep. Then we saw that the algorithm works in a set of phases. In the first phase, the algorithm wakes up all the processes, so that they can start participating in the election algorithm. So, this is done by the following piece of code, that if P is initiator, then it sets WSP equal to true, and then for all q belonging to neighbor of P, it sends the wake up to q. And then when a node receives a wake up, this is what it does, that while WRP is less than the number of neighbors of P, it receives wake up and then increases WRP by 1, and then if not WSP, that if WSP is not true, then it is receiving the first wake up call, then it sets WSP equal to true, and then sends every neighbor a wake up. Okay. So, if you look at it, this is how the thing is going to work. Let me take an example and show you that. Suppose we have this is the tree, and let us say that the algorithm is initiated here, right. So, what does this one do? It sets, suppose this is the process P, then the first thing that this one does is it sets WSP equal to true, right, and then for all neighbors it sends a wake up. Okay. So, after a node receives a wake up, what does it do? It first checks whether, suppose this is q, it checks whether WSQ is true, initially it is false. So, when it gets the first wake up, it will set WSQ to true, and then it will send wake up messages to all nodes, including the one from which it got the wake up, right, and it will continue to wait until it gets wake up from all its neighbors. So, it has already got wake up from here. So, it will wait until it gets wake up from this neighbor, wake up from this neighbor, and wake up from this neighbor. When it gets wake up from all of them, then its wake up phase is over, then it can go into the election part, right. Now, let us see what happens when the election algorithm starts. After everybody is woken up, after a process is woken up, that is, it has done the needful, it has sent out the wake up calls and got back wake up calls from all the neighbors, then let us see what it does. Then we look at two types of processes. So, those processes for which the number of, so RECP queue is basically an array of flags kept in P to indicate whether a token has been received from the neighbor Q or not. So, RECP queue indicates whether a token has been received from Q or not. So, for all neighbors of P, RECP for all neighbors j of P, RECP j is initially false, right. Now, what we are doing here is we are checking whether the number of neighbors for which RECP is false is greater than 1. If not, then it is a leaf node. Why? Because for the leaf node there is only one neighbor. So, the algorithm actually starts, the election part of it starts when the leaf nodes send a token with their own IDs to their neighbors. Okay. And then they receive token from the neighbor. So, again just like we had for the wake up, the tokens will be sent out and received. Okay. So, the leaf is sending it to its parent, and what is the parent doing? Parent will get tokens from all the children in the tree, and then its this thing is going to become equal to 1. See, when the node P has received tokens from everybody except 1, then it will come out of this while loop, and then it will send the token to the remaining node, right. And in whenever you get the tokens, you always compute Vp to be minimum of Vp and the value that is contained in the token, right. All right. And then this is the place where the last token is sent, this is the place where the last token is received, and again you do Vp equal to minimum Vpr, right. Now, that you have received tokens from everyone, you check whether Vp is equal to P. If Vp is equal to P, then P declares itself leader, otherwise the state of P is lost, that is, it has lost the election. And then after this step, for all q belonging to neighbor P, q not equal to q0, we send the token Vp to q. Okay. Yes.
Sir, once it's send, once the leaf node is sending this token to q0 neighbor, then it will immediately receive a reply.
Once a
leaf node, the leaf node sends token Vp to q0.
Yes.
Now, q0 will immediately send it back on.
No, not immediately. So, let us take an example and see how this works, right. Can you see the node numbers? Right. Now, this is where the algorithm, this is how the algorithm will work. So, initially after the wake up is done, which node will, which are the nodes which will start sending the tokens for the first time? The leaf ones, right, because for the leaf ones the number of neighbors with which we have not, from which we have not got a token is only 1, right. So, they are going to send token to their only neighbors, but the token will be loaded with their IDs. So, this one will send a token with 6, this one will send a token with 2, right, this one will send a token with 3, 7, now see at this point 5, 4, 8, 9, 1 they are not going to send anything, because for them they initially the number of neighbors from which they have not got tokens is more than 1, right. So, they are not going to do anything at that point of time. Okay. Now, when 5 gets both 6 and 2, then now 5 satisfies the condition that the number of neighbors from which it has not yet got the token is 1, not greater than 1, right. So, after it has got 6 and 2, at that time 5 can send a token, right. So, let us see what is it going to do. It will send token to the neighbor which is not yet, from which it has not yet got a token. So, it is going to take the minimum of all of this. So, minimum of 6, 2 and 5, right, and it will send. So, that becomes V 5. Okay. Now, at this point of time the value of V 5 is the minimum of 6, 2 and its own 5. So, it is 2, and it is going to send a token to whom? To 4, right. What is 8 going to do? Between 3, 7 and 8, 3. So, it will send 3, right. What is this going to do? 10, 12 and 1, it will send 1. Okay. Right. Now, at this point of time 9 qualifies to participate in the election, because now for 9 only one neighbor is from which it has not got a token. Similarly, 4 can also participate. So, what will 4 do? It will take the minimum of 2, 3, 4. So, that is 2, and it will send 2, and this one will do what? 11, 1 and 9. So, 1. So, it will send 1, right. Now, let us see where is 4 in the code. In 4, the node 4 has sent the token to the only remaining neighbor from which it has not got a token, and then has received a token, right. So, here the node 4 had sent the token with 2 and has got the token with 1, right. So, it will again do VP is minimum of this. So, it will update here on receipt of this message, it will update V4 to 1, right. But see, at this point of time it has got tokens from all its neighbors, right. So, it checks whether V4 is equal to 4. Well, it is not. So, it declares itself as a loser. It knows it has lost the election, right. But now it also knows that these people who had sent 2 and 3, they do not know that 1 is there, right. So, the algorithm cannot terminate here. So, they have to the 4 has to tell these people that, look, I know that 1 has won the election, but you people also need to know that, right. So, that is why what it will do here is that for all neighbors of P except the one from which it got this minimum token, it will send token Vp to Q. Okay. So, what is it going to do? It will send 1 to this, 1 to this. Now, let us see what 8 is going to do. Now, 8 has got the minimum, has got token from all its neighbors, right. So, now 8 is going to compute V8 is 1, right, but it can't stop there. So, it will send 1 here and it will send 1 here. Now, this one will update itself to V7 to 1 and this one will update V3 to 1, right. Similarly, this is when this is received, then V5 will become 1 and then it is going to send this 1 to these 2. So, V2 will become 1 and then V6 will become 1. So, in this side everyone now knows that the leader is 1. Now, let us see what happens on this side. When 9 gets this 2, it will compute the minimum of all 3. So, V9 will become 1, right, it will become 1. Now, what it has to do is it has to send 1, this one, to all except the last one which it got, right. So, it will send 1 to this, 1 to this. Now, see, it is very important for 1 to get this 1, otherwise it will never realize that it is the leader, right. You have to have the permission from everybody saying that you are the leader. Okay. So, now once 1 gets this, it sets V1 to 1 and then this criteria that Vp equal to P is satisfied. So, this 1 declares itself as leader, right, but it again has to inform the other neighbors, it has to send 1 to the other neighbors. Once that is done, then V10 will become 1 and V12 will also become 1. At this point of time, all processes know that 1 is the leader. Is it okay? Here everyone is contesting the election. Right, right. So, it will assume its Vp to be arbitrarily high. It will assume its own ID to be arbitrarily high. If it is not contesting the election, then it will just assume that its own ID is arbitrarily high, it is infinity, let us say. Right. If you set your own ID to be infinity, then you are as well not contesting the election, right. Okay. Now, see what effectively happened here was that we can think of this as a kind of wave algorithm. Every node sends out its own wave, right. So, 1 sends out its wave in this direction and that wave actually propagated to all nodes, right, and then came back here and then propagated to this side, right. We will generalize this concept for getting an election algorithm for general networks. We will do it in the following way. What does a wave algorithm do? You remember the echo algorithm? What does it do? It propagates out messages to all nodes in the network, right, and then the replies come back from everybody and the initiator knows that replies have come back from everybody. So, the algorithm can terminate, right. By definition, the algorithm is going to terminate only after there is some causally preceding event in every process, right. So, that is the echo algorithm that we studied previously. Now, suppose we do it this way, that every contestant in the election will start its own version of the echo algorithm, okay. And all messages in that particular echo algorithm, which is initiated by a process P, all messages for that wave will be labeled with P, so that you do not confuse between two waves, right. Now, a node, when it receives a wave having higher ID than the previous wave, then it will not propagate the wave. Now, you see, if it does not propagate the wave or does not participate in the wave anymore, then that wave will never terminate. Why? Because the initiator of that wave will never get all the replies back. Okay. This is called extinction. A wave which is worse than the best wave will become extinct at certain point of time. Where will it become extinct? When it meets the other wave. So, the best wave is going to propagate all through all the processes and terminate. Any of the other waves, when it hits the frontier of the best wave, will get damped there, right, and it will not propagate any further, and so it will not terminate, all right. And then when the best wave terminates, then the initiator of the best wave will realize that I am the leader, because my wave has come back and no one has blocked it. So, it will terminate, and then that initiator will again send out messages informing everyone with another echo algorithm to declare itself as the winner. Is that clear? I mean, the philosophy of the whole thing, right?
How would they come to know at what point of time that their wave has been stopped?
They will not know, but when the leader messages come out from the initiator, from the leader, they will know that they have lost, right. Before that they will not know.
What is the difference between leader message and normal wave message?
The leader message is the one which is a special type of message which is sent out after one of the contestants realizes that it is the winner. So, suppose I realize that my wave, when the wave terminates, you know, right. So, when your wave terminates, you know that you are the leader, then you send out leader messages to everyone informing them that I am the winner, right. And those which were other hopeful contestants, their wave had not terminated, but they do not know whether it will terminate or not. When they get the leader message, they know that their waves will not terminate because they have lost the election. Okay. Now, let us see how we implement this. So, this is the echo algorithm which is familiar to us from previous classes, that the initiator starts by sending token messages to all neighbors, okay, and then waits to receive token from all the neighbors and then decides, right. And non-initiators, when they receive their first token, they set their father to be the node from which it receives the first token, and then sends out token messages to all other neighbors except the father, and then waits for receiving token from all those other neighbors. When all those other neighbors send token to the process P, then it sends a token to its father. Okay. That is how the echo algorithm works, right. Now, this is how we will use extinction on the echo algorithm. So, let us look at the set of variables that we are going to use here. The first thing here is CAWP. Now, CAW stands for the currently active wave. This is the currently active wave. Initially, it is undefined. Okay. Then we have receive P, which is the number of token CAWP received. Okay, number of tokens received in the current wave. Now, if the current wave changes, this will again be reinitialized to 0. Okay. So, we will see how this thing happens. Father P is the father of the process P in the wave CAWP, in the currently active wave. So, at every point of time a process is in a currently active wave, right. So, if any wave which is worse than the currently active wave comes to the process P, it will not respond to it. So, it will damp it, right. But if a better wave comes, then that becomes a currently active wave and it will now start participating in that currently active wave and abort all activities in the previously currently active wave. Okay. It will not participate anymore in the previous wave, it will forget about everything about the previous wave and completely switch over to the new better wave. Okay. That is why you see father P, REC P, these are all defined with respect to the currently active wave. And LREC P is the number of LDR messages received. LDR is the leader messages which will be sent out after the winner has decided that it is the winner and it is sending out messages to everyone with these LDR messages. These are leader messages. And win P is the identity of the leader. Okay. And at the end, all processes must agree on win P. So, win P equal to win Q equal to win J equal to win I has to happen. Okay. They all must agree on the same leader. Well, now let us see how the algorithm starts. If P is the initiator, okay, if P is initiator, is not the initiator because there can be many initiators. All the contestants will be initiators. Each contestant will start its own wave, right, like its election manifesto or propaganda, okay, and then that will spread, right, and the one whose propaganda is the best will win, right. So, fair enough. So, if P is the initiator, then currently active wave P is equal to P, because it is starting the algorithm here. Then for all Q belonging to neighbor P, it sends token P to Q. Now, note that along with the token, it sends its ID. Okay. Then while LREC P, what is LREC? Number of leader messages. Okay. Now, see, this is one code which has everything, right. So, you have to understand it that when you write the code for a distributed algorithm, your algorithm will be like this, that for each type of message what do you do, right. Now, you know that some types of messages you can receive before some other type of messages, or you can receive them in any order. So, therefore, your algorithm has to be written in such a way that you may receive this message first or that message first, regardless of that you should do the consistent thing, right. So, let us see here, that is why you see before we have anything else we have this LREC P, which actually refers to the last phase of the algorithm, when the leader is being declared. Now, if LREC P is less than the number of neighbors of P, then we receive some message from Q. Now, when LREC P is equal to the number of neighbors of P, at that time you do not have to do anything else, right, because you have got the leader message from all your neighbors, right. So, that is where you actually terminate, right. So, this is before that happens. So, you receive message from Q, the message can be what types? It can be a token message or it can be a leader message, right. If the message is a leader message with R as the leader, then if LREC P is 0, that means that this is the first leader message that it has got, right. So, now remember that the leader the wave containing the leader message is also a leader, it is also an echo algorithm, right. So, it is exactly as in the echo algorithm, that what it does is it checks whether this is the first message received of this type, then it will send to all neighbors this leader message, okay, and then increment this and set win P equal to R, because the leader message asserts that R is the winner, right, clear. Now, if on the other hand, if the message received is a token message, then we do the following thing. If R, the identity of this wave, if it is less than CAWP, if it is less than the currently active wave that P knows about, then now this is a better wave. So, what is going to happen? P will completely switch over, right. So, it sets CAWP equal to P. Now, it reinitializes rec P to 0, okay. Why? Because it is a fresh wave that it is receiving and it will start participating in this one, and in this fresh wave, who is the father of P? Q. The Q is the node from which it has got the message. So, receive message from Q. Q is the node from which it got the message. So, it will set father P equal to Q. Then, for all S belonging to the neighbors of P such that S not equal to Q, it sends token R to S. So, it propagates the wave. Okay. Which one? Oh, yes, this is a typo, I am sorry, this should be R. Okay, let me correct it, just hold on. Yeah. So, the currently active wave becomes R, and then we propagate the wave by sending token R to all the neighbors except the parent in that wave, right. Now, look at the second possibility. This is a possibility where, oops, just let me choose the pen once again. Okay, so this is the case where we have R is less than CAWP, right. Now, suppose if R is equal to CAWP, then this message is a message of the current wave, right. So, then you see this is not the first time that it is receiving this message of this current wave. So, its parent is already defined, its parent in the current wave is already defined, because this is not the first message that it is receiving in the currently active wave. So, it increases RECP by 1 because it has got now another token message of the same wave. It checks whether RECP is equal to number of neighbors of P. Now, if so, then if CAWP is equal to P, then for all S belonging to neighbor it sends LDR P to S. Now, let us understand this part carefully. Which is the node which is going to discover this? That the number of tokens received for the current wave is equal to the number of neighbors. Only the initiator of the currently active wave can see this, right? Right? Why? Because for every other node it will get tokens from all its children, right? For other nodes also it will happen at the end, right? So, let us understand this. Let me show this. So, in the currently active wave, what happens is this node sends out the wave to its children, right. Now, a particular child, it will propagate the wave out, and then when it gets token back from each of them, at that time, suppose this is P, at that time the value of RECP will be equal to number of neighbors, right, of P, because it has got token from its parent, now it has got token from all of its children. So, RECP has become equal to number of neighbors of P, right, and at this point of time it is going to send token back to its parent, right, and for the initiator, parent is itself, and moreover it will see that the token, see this token has some R. Now, if it sees that it itself is R, then it knows that its own wave has terminated, right. So, it will declare itself a leader and start the leader messages, the wave containing the leader messages, right. Now, that is what is happening here. After receiving the message, if it sees that the number of neighbors of P is equal to RECP, then it checks whether CAWP is equal to P. If it is equal to P, then it is the initiator of this wave and the wave has terminated. So, it is going to start sending out the leader messages. So, it will send leader P to all its neighbors S, and that echo algorithm will now start, all right.
So, it may happen that even after this again another set of messages come from another side, that this is, and then it realizes that it is cancelled leader.
It cannot happen, because you see its own wave can only terminate after it has reached all other processes, right. So, it will hit the wave, the frontier of the other waves somewhere or the other, yes. If its algorithm terminates, if its echo algorithm terminates, then it knows that no one disputes its leader, it as a leader, right. It is like this, that I go around telling everybody, look, I claim to be the leader, and anybody who disputes that blocks my wave. So, my wave only terminates when everyone agrees that I am the leader, right. Now,
Now understood that when it checks that when RECP becomes equal to number of neighbors, and at that point of time it checks if the currently active wave is equal to P. How does it conclude that I am the leader? I don't understand this part.
okay, see, let us get this thing, let us understand this thing very clearly. the algorithm is working in this way. Suppose at a these are the contestants. Okay. Each contestant is an initiator of its own wave. Right. Besides the contestants, we can have other nodes also. We can have some non-contestants also. Now, what happens is each contestant is sending out its own wave. So, its wave is going out, right. Similarly, this contestant is sending out its own wave, right. How do you detect the termination of a wave? When the wave propagates out, reaches all processes, and then replies come back, and then the initiator, the decision that the wave has terminated is taken at the initiator of that wave. Now, any intermediate node where this wave reaches and then at some point of time this wave reaches, this is not going to propagate both of them. The one which has received the better one, let us say the red one is the better one, any node which has propagated the red one will never propagate the blue one, right. And so, the blue one will never terminate. So, if this node sees that its wave has terminated, it means that there cannot be any other active wave in the whole distributed system. All other active waves have been damped, right. Then it declares itself a leader. But these nodes, they do not know which is the leader. Why do they not know? Remember that the best wave, this red wave had reached them. So, if their currently CAW is actually this red one, right, but they still cannot decide that the red one is the leader. Why? Because they do not know whether another wave is coming or not. That there is no other wave which can defeat this wave is known only to the initiator of the wave, because it is able to terminate, right. No one else knows that there is not any other wave in the distributed system which is going to come, right. So, therefore, it is up to the leader to assert that it is the leader, and that is why the leader messages are sent out.
So, it was initiator was one which was contesting for election.
Every contestant is an initiator of its own wave. So, if there are 5 contestants, there will be 5 different waves: red, green, blue, yellow, white.
So, that the node which is not contesting, that can also decide, block the wave, because
It will. Every intermediate node is maintaining a currently active wave, and once it has got a wave of value V, it will not propagate any wave which has a higher value, right. Clear? So, let us see, right. So, let us come back to this point. When you see RECP equal to number of neighbors of P, and you see that the currently active wave P is P itself, then these two together tells the process P that its wave has terminated with success, right. So, P now sends out the leader P messages. Now, suppose you find that you have received tokens from all your neighbors, but CAWP is not equal to P. That means that your job in this wave is over, but you are not the initiator. But if you are not the initiator, then you have a parent in this wave. So, you send the token CAWP to the father of P. Okay. And thereby your work in this currently active wave is over, right. Now, we looked at two cases, R is less than CAWP, in which case P switched over to the new wave, R is equal to CAWP, in which case it behaved exactly as in the echo algorithm for this current wave, and the third one is if R is greater than CAWP. So, you have got a token message for a wave which is worse than the current active wave, then we simply ignore the message, and that is how extinction applies. You just simply throw away that token message, you do not propagate the wave. If you do not propagate the wave will not terminate, right. So, this is the third thing, the extinction. Okay. So, then the wave R becomes extinct. Then finally, at the end of this whole thing, if win P is equal to P, then state P equal to leader, else state P is equal to lost. Okay. Now, what is win P? Who sets win P? Where did we set win P? Here. Okay. This is where you set win P, and except for the initiator of the leader messages, everyone else will be lost. Is that clear? Okay. Now, I will ask you to do a few things. Okay, okay, just one. This is a simple result, that if A is a centralized wave algorithm using m messages per wave, the algorithm EXA, the algorithm EXA is the one that we talked about, the extinction algorithm, elects a leader using at most nm messages. Why? Because each of the n processes, can start a wave, and they can have at most m messages. So, it is fairly obvious that the number of messages will be at most nm messages, and the fact that it actually elects a leader follows from the fact that the wave of the leader is only going to terminate, and therefore, it will declare itself as a leader and then use another wave to inform everyone that it is the leader. Okay. So, that is also fairly simple way of looking at the proof of correctness for this algorithm. Right?
Receives also replies.
Which one?
In this wave algorithm, is getting a reply also from not reply.
Token. There is only one type of message, token. If you brush up the echo algorithm, you will not have any more doubts on that. Right? The echo algorithm is the standard wave algorithm that we are using here. Right? Now, what I want you to think about is that we looked at those algorithms for leader election in rings, right. What about using extinction on those? Suppose we use the notion of extinction on that, right, where what did we do in that the first algorithm, where we just pass the token, every contestant pass the token along the unidirectional ring, and whoever gets its token back becomes the winner, right. Now, what if we use extinction there? What happens if we use extinction there? Does it reduce the number of messages? What happens if we use extinction in Hertzberg-Sinclair algorithm for rings? Okay. What happens if we use the notion of extinction for leader election in trees? In some of them you will see that extinction will help, in some of them it will not help, right. But it is a good exercise to think that where extinction is useful. In this case, it is definitely a very simple algorithm which is useful in practice, and because echo algorithm does parallel propagation of the wave, so it terminates pretty fast. So, this is one of the preferred algorithms for leader election. Right. So, with that we come to the end of this chapter for leader election, and we might do a few more things using some of the leader election algorithms in the lectures that will follow.